Welcome to session 3 on digital circuit design using ADS. I'm Anurag Nigam. So in last session I had demonstrated the characteristics of a CMOS inverter. Very quickly I'm going to show you how to recreate the circuit using 7 nanometer FinFET, and let's see what's the performance in terms of speed of that 7 nanometer FinFET. Okay, so I'm going to name them the same. So I will call it uh, Nand Gate, and I'll have a prefix of HS, which refers to high speed. Okay, so I'm going to create a schematic. Now what I'm going to do is, because I want to keep the pinout same, I'm going to just copy the schematic of this one, right? Because I want to keep the symbol and pinout same so that I can very quickly create circuits later on for high speed, so I don't have to do a lot of different stuff. So I'm gonna just paste this over here throughout this one and this one, and I want to put here BSIM-CMG, right? So what I'll do is I'll go to devices MOS, and under this there is something called BSIM-CMG P and N. So this is BSIM-CMG P, and I will mirror this out and connect it over here, right? So this is a P model, and then I'm going to do a BSIM-CMG N model, right? So this will be the N one, right? Now what I'm going to do is, the way it is modeled, I'm going to set some parameters. So this will be PCMG for PMOS, right? This will be PCMG, and what I will do is number of fingers is 1, and fin as, let's say, 3, right? And thickness is 5 nanometer, so this is going to be 5 nanometer. Okay, so let me say okay. Let me pause the video to check some things. Okay, so what I'm going to do is, now I'm going to edit some of the parameters. So first of all, I'll clear all the parameters being displayed, and then I'm going to just show the parameters which I want to show. And this is 5 nano, and this is okay. So this is actually this every gate is a tri-gate, right? So there are 2 gates, and then there is a on the fin on the left and right, and then on the top there is another gate. So it's a tri-gate FinFET, right? And for NMOS, I am going to have the model as NCMG, and I'm going to display only the ones which I am interested in. Okay, so I'm going to display NCMG as the model, and fin as 1, and number of fins per gate is fins per finger is 1. Apply. Okay, so now I'm going to just display those also, and F1. So now PMOS is 3 times the thickness of the thin is 5 nanometer. So thickness of the fin is 5 nanometers. Okay, so now what you see is there is a PMOS device which is 3 times of the NMOS device. So we have this, and what I'm going to do is I'm going to just copy the symbol of the previous one, right? So I have this over here. Okay, I can just copy this symbol and paste the symbol in this cell, right? So I have a symbol for this, the same symbol I can use, right? Because the pin numbers and pin names are the same, right? And then I can test it. So I can even copy this test not, right? Copy cell, and I will what's the issue? Okay, so it's saying that you cannot. Okay, so that's not what's going to happen. I am going to copy the cell which is called test not, and test not HS, Okay, and choose a folder to copy it to be this high speed folder and say OK. Okay, so in the high speed folder I have this one. Okay, all I have to do is I have to change this to HS. So that's the advantage of using same symbol. I have just changed this name and the design got changed. Okay, so this is a trick. And then the loading cannot be more than 5 femto because it's a very small device which I'm going to drive, and I'm going to drive this at let's say 10 gigahertz. So this will still remain that. So 10 gigahertz means that this is going to be 49. Okay, 1 gigahertz is 1 nanosecond. So 10 gigahertz is zero point 0.1 or 100 picosecond. So 49 picosecond is the width, 1 picosecond is the rise time, and 1 picosecond is the fall time, right? 1 picosecond is the fall time, and I'm driving this at 10 gigahertz. Supply is still 1.8, right? And I am going to simulate for 0.5 nanoseconds, right? And I am going to simulate this at 0.1 picosecond, right? 0.1 picosecond. Okay, so now we are done. We just we need to put the things from here. These are the two models which I want to use. So I just going to copy these two models, Control C and Control V. So these are the two models which I'm going to use instead of this. Okay, so I have a PSIM CMG and NSIM CMG, and all I'm going to do is now hit simulate. Okay, okay, there is some warning here. So if I can manage notification and turn it off, or every time it will be there. Notifications off. Okay, so now what we have is A and Q, and it's the same inverter, right? It's the same response, right? But it's much higher frequency. You can see it's at 10 gigahertz, right? So now I want to zoom into this portion, and then you can do everything the same which we did for a 130 nanometer, right? And then you can find out the delay, and you can find out the rise time, fall time, and everything. Okay, so this thing is operating at 10 gigahertz. Now very quickly, now I'm going to go through all the gates one by one. Okay, so to do that, I can, to do this rapid kind of design, I can take this and say copy cell, and then save this as Nand Gate medium speed. Okay, so I think it got copied over here somewhere. Is it? Yeah, here. Okay, so I'm gonna modify this to a NAND gate. So to modify this to a NAND gate, all I have to do is just create some space here for this one, and I'm gonna copy this transistor, and I'm gonna paste this transistor over here. So I want to copy this transistor and paste it over here. Okay, so now what I have is two transistors, as we have discussed earlier, right? Two transistors in this fashion, and then I'm going to introduce one more transistor in that fashion, like this, right? And I'm going to remove the tuning, because tuning was just to demonstrate you the symmetric nature of the design for pull up and pull down. So I'm going to remove the tune on this. So now what you have is, I'm going to connect this over here, and I have this one. So I have still got this as one input, and then I have one more pin which I will name as B. Okay, and that pin I am going to connect over here. So now I have got two input NAND gate. Only thing I'm going to do is I'm going to scale this up slightly. So let's make this 4. Let's make this 4. This is because they are stacked together like this, and these come in parallel. Okay, so I can reduce slightly on these. Okay, and so this is the configuration, which will more or less be symmetric pull up and pull down. Okay, so I have to introduce pin 5 as B. So I'm going to just modify the symbol there. So this is the NAND gate, and its symbol is going to be another pin. So I have to insert a pin, and that will be pin 5, and it will be called B. And this is all I have to do, and I can just copy this text here as here. Somehow this is going to be off grid, so okay, so let's not copy this. It's not a good idea, right? Let's make a line, okay, of same size. That's okay. So that's going to be B. Let's name this as B. Okay, so that's B. So all I'm going to do is I'm going to move this slightly, and remove this guy, move the ground down, and I am going to design so everything is off grid, is it? So this is what happens. Okay, we will see to it, don't worry about this. Okay, so here, and I am going to choose this, going from here. Is this symmetric? I think it is symmetric, and this I want to be medium. Okay, and then I want to introduce an arc. Insert an arc like this one. Again, I want this to be a medium rather than thin. Okay, so that's there, and that's Q, and these I might have to adjust, so that's fine. This is ground, and this is VDD. So let's pull them back. Okay, so this is VDD, this is ground. Okay, so all I'm going to do is turn off the grid and get this up to here, and get this one up to here. So this one slightly adjusting it. Okay, this VDD closer, this ground closer. Okay, so I'm going to turn back the grid on, and I have a NAND gate. Okay, so once I have a NAND gate, okay, this is using 130 nanometer devices, right? So I am going to quickly make another version of it after testing it. So I'm going to take the test nor and say copy cell. Test not I will make as test not as test NAND medium speed, and I'm not going to copy these, only this one I'm going to copy, and the library I'm going to copy is to medium speed. Done. So this is my test NAND MS, and here I am going to change this to NAND. Okay, so that replaces that. That's my supply. So that's my supply, and then that's my one of my inputs is over here, right? And then I'm going to introduce a B input somewhere over here. Okay, so this is an extra piece of line. Okay, so let's just copy this and turn it into half the frequency. So basically this will become 0.5 gigahertz, and this one will be 2.4, right? 2.4. Oh, sorry, it will be twice, right? So it will be 9.9. Sorry, 99. So that is the time period, and I'll just connect this over here and call this as, sorry for this, call this as B. Okay, so now I'm ready for simulation. One of them at 1 gigahertz, other is at 0.5 gigahertz, right? And these are the two inputs, and then this is the output, right? And remaining remains the same. Okay, so I'm gonna hit simulate button. Okay, once I'm done with this, I want to look at the two inputs are A and B, and then I want to look at Q, right? So I'll split the traces. So if you double click it and say this one, it is going to split the traces, this, right? So I'm going to take and scale all of them to be the same scales, right? So basically go to trace options. So I want them to be same scale. So if I go to bottom y axis, right, so this is going to go from 0 to 2 like the others, right, and steps of 0.5. Okay, so that's there. So I'm going to change this color so it's better visible. So this is going to be your NAND response. So NAND output, if you look at the truth table, okay, the truth table says that the NAND output is low when both inputs are high. So this is what is happening over here, and for all other cases it's high. So this validates that this is the truth table of NAND gate. Now one interesting thing I want to show you is, if I want to display the truth table, right, so I can do this. Okay, so now what is happening is I'm looking at index n. So let's put an equation. It says n is equal to find index, and then I am going to look into time. Okay, and I'm looking into independent of m1. So they should return me the index of n. So let's display the index of n under equations. So let's see what is n. Okay, so the n is 252 here. If I move it, the n is going to change. So this is the sample number, right? So that's fine. So once I'm done with this, I can write some equation. Okay, for example, I can say I want to display, right? So I want to say a d, for example, AD is equal to, so I'm going to write a if statement. If okay, so this is going to be A of index n, right, is greater than, let's say, half the value, or let's say 1 volt, then I would say 1, else I would say 0, and then I would say and if. I think if this statement is correct. No, this statement is not correct. Okay, I think it should be and if. Okay, so let's refer to the function help. Okay, what I want to do is I want to display the truth table. Okay, so there is the function help, and I'm looking at the if statement. So I want to look at the if else statement or if statement, right? So if statement goes as if condition Let's look at another example. Not there. Else if condition then expression, else expression. There is no end. Okay, so there is no end. So I think if this is going to work. No, it doesn't. So let me just pause the video and figure out what happened. I just figured out what happened. Okay, so let's correct this one. So this index has to be a square bracket. Okay, so that was the mistake here, a common mistake. And then you don't need this, and you don't even need this, and you say and if. Okay, so that means that AD is going to be assigned 1 if it is greater than 1, else it is going to be assigned 0. So I am back into terms of zeros and ones. Similarly, I can write equation for B. So I can say BD is equal to 1 if BN, wherever your marker is that. And then similarly, I will do it for QD. So basically QD for display, actually D for display, is QN is 1. So now I am going to put this in a display. So here if I go to equation, if I say AD, BD and QD, and I don't have any independent value. Okay, so now I'm saying that if both are 1, then Q is equal to 0. Okay, so these equations are going to be very helpful to check the results in a waveform. So if I move to the other side, like if I move to another option where I have got 0, 1, and then the answer is 1. Then if I go to 1, 0, the answer is 1. And if I go to 0, 0, the answer is 1. So basically that validates your truth table, right? So this is very simple to write, and you will be able to verify your truth table. So this is with the NAND gate. Now I'm going to very quickly turn this into a I'm going to turn this NAND gate into a high-speed NAND gate. So if I take this NAND gate and say copy cell, and I change this to HS, and then copy this into a high-speed folder and say OK. So now what I have done is I have got a high-speed NAND gate here. All I have to do is modify this. So now what I'll do is the following. I am going to copy these transistors from NOT gate and copy them over here and replace them. Very simple. So that I will have a high-speed NAND gate. Okay, so there you will have PMOS devices, right? And I will just say Control C, Control V. So we have PMOS devices, and then I'm going to have NMOS devices. Okay, I'll say Control C and Control V. So this one has to be replaced by this one. So this is a high-speed variant of that. I am going to change this to 2 and this to 2, and I'm going to change these to 4 and 4. So this is arbitrary sizing, you might say, but you get an idea of pull up and pull down currents after some point of time. So this is done. Okay, one more thing I would do is the following, that I want a distinction, what is a high speed and what is a low speed. So usually I am going to change this symbol and add a piece of text here. Insert text, and I will put here HS. So HS means it's a high speed. So in case HS is not there, that will be a medium speed, and in case HS is there, that would be called a high speed. So insert text. Where is the text? Here. I will insert a text here, HS, high speed. Okay, so now I have made 2 gates which are high speed gates. Now same thing I'm going to do with the NAND here, is I'm going to copy the test bench for NAND. Or rather, if I want, yeah, that's fine. I'm gonna say copy cell and test NAND. I'm going to say test NAND HS. Okay, and I am going to copy this in a high speed folder and say okay. So once I'm done with this, okay, so there will be a NAND gate here, test NAND HS. So in this case, I can change this to HS, and you'll see that that HS has come here, so that means that's a high speed one, and this is a 10 gigahertz. So this is going to be so 149 picosecond is this 10 gigahertz. Rise time as 1 picosecond, fall time as 1 picosecond, and then I'm gonna do 5 gigahertz over here. Okay, and this would be 99 picosecond, and this is going to be 1 picosecond, and this is going to be 1 picosecond. So I have changed all the sources. Okay, and then I'm going to simulate for 0.5 nanosecond in steps of 0.1 picosecond. Okay, so now I'm ready to test a high speed NAND gate. I'll hit simulate. Okay, there is an error because I haven't placed the, so I will go and copy these two, say Ctrl C and throw this out, Ctrl V, place it over here, escape, and then hit simulate again. So fine, no issues here. And I'm going to copy the same schematic, same data display, because I don't want to keep changing the data display, right? I don't want to write these equations. So I'm going to copy this stuff, and whenever the display opens, I'm going to paste it over there. Okay, so I'm going to do a Control V here. So this is done. Okay, so now you can see. Okay, one more thing I want to do is, this is 5 picosecond, 5 femto, sorry, because these devices are small, so they are not going to have a lot of drive capability. That's why you have this sloping stuff, right? So once you do a 5, it will be okay. But the logic is still correct. When both inputs are high, the output is low. And the circuit is operating at 10 gigahertz. Let's this finish. It'll update it. Okay, so now it looks better, right? Okay, so 1 1 0, in here it is going to be 0 1 1, and over here it is going to be 1 0 1, and over here it is going to be 0 0 1. So this truth table is verified. So basically this is a high speed NAND gate. So we are done with this. Now the next thing I'm going to do is convert this into a NOR gate. So to convert this into a NOR gate, what happened? Just copy this to high speed. Okay, so to convert this into a NOR gate, let's look at this. Okay, so this is the one. I'll say copy cell, and I'll change this to NOR. Okay, and it will go under medium speed. Fine. So it's over here as a NOR gate. Correct? Oh, I opened a NOT one, sorry. So this has to be modified to a NOR gate. So to do that, all I have to do is rearrange the transistors in such a fashion is this will come over here, and this will come this way, and this thing, okay, so I'm going to disconnect this, and this transistor will come over here, and this output pin would come over here. So this is going to be a very quick turnaround, converting the gates to a NOT gate, to a NOR gate, to input NOR gate. And this is going to be one of the inputs, and this is going to be another of the inputs. So this is modified into a NOR gate, right? So all I had to do is these are in stack 4 4, and this has become big, so that's fine. So I'm just gonna leave it as is. Okay, so that's my NOR gate, and then I'm going to change the symbol for this NOR gate, right? So this symbol has to be changed, right? It should look like a NOR gate, right? So I'm going to say arc, insert arc clockwise. So let's say I'm going to start from here. That's going to be too much of an arc. Insert clockwise arc medium. Then okay, doesn't matter, let's do it this way, and then copy this, make a copy of this, invert it out, and that's over there, and this thing has to move out, right? So this thing has to be placed over here, so it's not matching, that's fine. And then I need an arc going from here to here. So this I want medium also, not thin. Okay, so I need to adjust these slightly, right? So I need to turn off the grid. So I am going to go to turn off the grid, options, turn off the grid. First thing I'm going to adjust is the following. I am going to shrink this here so as to adjust this guy over here like this, and hopefully it is centered. Okay, so if it is not, really doesn't matter. So this is centered, this thing is Q, and then I'm going to extend this to meet over here and over here, and this is A, and this one is B, and I'm going to turn on the grid again. Okay, so I have converted this symbol to a NOR symbol, and I'm done. So this is my NOR gate. So now I want to do a high-speed NOR gate, right? So to do a high-speed NOR gate, I can just copy this cell, copy cell to NOR gate high speed, and then I will copy it to the high speed folder, like this. Now if you remember, the symbol is not modified yet, right? And even the circuit is not, right? So you go to the NOR gate circuit, and what you do is you just get rid of these, which is going to be 130 nanometer, replace it by a 7 nanometer. So to replace this to a 7 nanometer, I'm going to copy them from Nand Gate. Okay, so I want to copy all these transistors. Okay, Control C, and then Control V over here, and I have to just connect them. So this is one transistor, this is another transistor, this is size of 4, and this is one transistor, and that's another transistor size of 4. So this is my high-speed NOR gate, and what I'm going to do is, the symbol is already I'm going to copy it. So let me just see. Okay, so this is a NAND gate, and this is the NOR gate, correct? Now I'm going to change the symbol, so I'm going to delete this symbol and copy the symbol from medium speed, NOR medium speed. So I'm going to copy this and copy this to NOR high speed. I'm going to paste it, and this I'm going to add HS over here. So I will say insert text and call it HS. Okay, so this is done. So now I'm going to test them. So to test, first I'll test the medium speed. So I'm going to say test NAND MS. I'm going to copy cell to test NOR MS. So I'm going to copy this to NOR MS, and it's in the same folder. It's done. So I have a copy NOR MS. I go to schematic and change this NAND to NOR, and we are done. So this is a NOR gate, right? And this is driving 15 picofarad, and I'm going to just hit simulate for this one. And I'm going to copy the display windows, right? So if I go here into the main window, less the display of NAND, I'm just going to copy this, Control C, and whenever the new window opens, I'll paste it over there. Okay, so I'm going to do Control V, and now you see when the input is high, the output is going to be low. So this is what an OR gate does. Over here again, 0 1 0 1 1 was 0, 0 1 was 0, 1 0 is 0, and here 0 0 is going to be 1, which is a correct truth table for NOR gate, right? So basically this is a test for a NOR gate. Now I'm going to similarly do a test for a NAND gate high speed. I'm going to copy this cell to test for a NOR gate high speed. Okay, NOR gate high speed, and I will say make a copy of it. So I'm going to test the NOR gate, right? So in this case, instead of NAND, I would have a NOR gate. So I'm driving with 10 gigahertz input and 5 gigahertz input. So I'm all set. I don't have to alter anything. I have to just hit simulate, and when the new window opens, I'm just gonna paste. Okay, so all I'm going to do is Control V, and it's the same, you see, it's the same response, right? I can check 1 1 is 0, 0 1 is going to be 0, 1 0 is going to be 0, and 0 0 is going to be 1, right? So this is still a NOR gate, high speed NOR gate, because it's operating at 10 gigahertz, and that's the end of the story here. So I have tested a high speed NOR gate. So basically I have got all the ingredients for NAND logic or NOR logic. Now if I want, I can do a XOR gate, but it's not worth doing it, because the XOR gate the number of transistors required will be 4 for a pull up and 4 for the pull down, so you will need 8 transistors. Now the same thing can be implemented using transmission gates, in which you will require 2 transmission gates, so that will be like 4 transistors, and 1 NOT gate, so that will be 6 transistors. So instead of 8 transistors, you can work with 6 transistors in case of a transmission gate. So I'm not going to implement the XOR gate in static. I hardly use XOR gate in static, so I'm not going to do that. Okay, so this basically completes my session, a quick session on the universal gates, right? So this is a high speed, it will go over here, and this is a medium speed over here. Okay, so I have quickly concluded the session on static gate designs, right? Thanks a lot. Thank you.